as the solvers we have in Drake. So that was my thinking. I mean, I think the computation time was about the same, probably. Maybe DeepNote made it a little slower. But yeah, I'm curious. I mean, I think some people who are very familiar with PyTorch didn't like that I do batch on the second axis instead of the first axis, right? But I hate that NumPy does it on the other axis because, you know, if I have a vector x, right, and I want to multiply it by a matrix Q, I don't, you know, if I have a batch x, I just want to have it like this, you know, for sure. I always want to put it on the second axis because then Q times x still makes sense, right? For me, it's like wrong to put the batch variables on the first index. But I know if you're used to NumPy and everything, that's frustrating. So anyways, please send me feedback as you guys have those comments and everything like that. I'm very curious what people like, what would help you learn the best. I mean, there's also, of course, performance things happening behind the scenes. Like Eigen in C++ uses column first ordering, and NumPy does row-wise ordering. So I'm playing some efficiency games too. But I just like batch on this axis better. OK. But that's all fun stuff. You guys up on the stream or not? Yes? OK, awesome. All right, so last time we started developing, I'd say maybe a new superpower, you know, of trying to understand how to be able to verify very non-trivial functions for all x, not just type of problem. And there's a second one, which is stop, you know, coming up with these Lyapunov functions out of nowhere. We're going to actually search. We're going to have the solver find the Lyapunov function for us. OK? And then, well, we start with global verification. We're going to, in global Lyapunov functions, we'll try to do the local version too, the regional version too, where we can only certify Lyapunov conditions over a certain domain to demonstrate regions of attraction. Talk about robustness and multibody. OK? So the big idea, there were a couple big ideas, but the big one that I started with last time, should really wear proper shirts. We went from dj dt equals, you know, a partial differential equation to an inequality dv dt. Right, and we change the complexity class. Was that we're going to go from verifying the conditions at a bunch of sample points and you see that, you know, this first one was required to make the second one useful or to practical, right? Because solving the class of functions that are the solutions to this complicated partial differential equation is an arbitrarily complicated class of functions. I don't know how to parameterize that set of solutions perfectly with equality, right? But if I relax it to an inequality, then relatively simpler functions, like polynomials up to degree 4 or something, can satisfy this for all x. I couldn't satisfy equality for all x, but I can satisfy inequality for all x. Okay, so those two work together. And the way I motivated this, and the key idea behind it, is that we already know examples of how to do that, right? When I wanted to say, for instance, for all x, x transpose px is less than or equal to 0, I can do that by just checking the eigenvalues of p, right? Which is a finite amount of computation for p, and it verifies for all x, right? And then the sums of squares, which we're going to go through from a slightly different perspective today, is the generalization of that to where I think about like this, okay? But it's still parameterizing it and doing a decision based on a finite amount of computing, and trying to just verify the eigenvalues of that matrix, but we do it with semi-definite programming. Okay, is that any questions at the high level? So we talked about, using the tools from convex optimization as a powerful set of tools. And although I could compute the eigenvalues directly, in the case of even the quadratic form, we said that writing constraints of the form like this, where the decision variables are p, this is a convex constraint. And the class of problems that solve it is the semi-definite programs, SDP. The generalization of that, which is still a semi-definite program, it's just leveraging this, but it gives us a new modeling tool where if we want to say now that if I have f of x or v of x, I'll use v, I guess, since it's going to be more similar to what we want to do, where v of x is a polynomial. Let me even write alpha here, a polynomial with coefficients alpha. It turns out that saying that v of alpha of x is sums of squares is also a convex constraint. It's from sums of squares optimization, which is also just a layer on top of SDP. Right, the commercial solvers only know about how to solve semi-definite programs, but because this ability to just write a constraint saying that I have a polynomial and I want it to say that it's greater than or equal to 0, well, that it's sums of squares, that's such a useful constraint that in the layer of Drake in this case, or some other higher level optimization packages, they allow you to write constraints in this form. And behind the scenes, they will generate the semi-definite programming constraints and decision variables for you and hand that down to the solver. Okay, so from the perspective of the solver, it's just a semi-definite program, but the modeling language lets you write things in this higher level, just saying that this polynomial is sums of squares. Okay, and let me just be super careful. If I say v of alpha of x is sums of squares, that implies that I can write it as the sum of things that are squared, right? So that's what the sum of squares means. So it definitely implies that for all x, v alpha of x is greater than or equal to 0. if you have a positive sum of these squares, then we have positivity, okay? But there's an interesting question about the converse, right? And the answer is, in general, that this is not true, that if v of x is greater than 0 everywhere, is it definitely a sum of squares polynomial, okay? That direction is in general no, but in practice, it doesn't seem to be a problem. But the gap, you actually have to work very hard to find a polynomial that is everywhere positive, that is cannot be proven positive as a sums of squares. There's papers written, there's famous polynomials by names. The Motzkin polynomial is a very famous polynomial which has this property. It's true here, but it's false here. Okay, but for the purposes of what we're doing, especially with Lyapunov, because many Lyapunov functions can prove, we're going to use these as if they're almost synonymous. But you just have to, I want you to remember that there's a gap. There are special cases where the answer is yes, but in the general answer is no. So this becomes a modeling tool, okay? Just like I can put constraints of the form p greater than or equal to 0, and then I can also, because the p's are my decision variables, I can still also put different convex costs and constraints on the elements of p. I can do the same thing here. I can do v of x as sums of squares as a constraint, and then I can put additional costs and constraints on the coefficients alpha, the coefficients of my polynomial, right? So you understand that the polynomial is, for instance, alpha 0 plus alpha 1 x plus alpha 2 x squared, right? These are the coefficients. Importantly, a polynomial is linear in its coefficients. And so I can, and I can take and put constraints on those, or costs on those coefficients that are convex. So the crazy 6-hump camel I showed you yesterday, just to say it, what happened in that example more carefully, right? So I keep saying yesterday. I know it was Tuesday. I just somehow can't get myself to say 2 days ago. I had a polynomial in 2 variables. Remember, I drew a plot. It was a 3D plot where the z-axis was the value of the polynomial, and it was a function of 2 variables. It happens to be a fairly simple polynomial, the famous 6-hump camel. Right, just like not a bad function and polynomial, but it had lots of local minima, 6 of them. Okay. And I have this oracle now, which says I can write a convex constraint asking if polynomials are sums of squares. So if I wanted to find the minimum of that 6-hump camel, the first thing I can do is I can just say, what if I tried to say, p of x, y minus some gamma is sums of squares. Okay? And I'm going to minimize or maximize. I'll minimize over gamma, negative gamma. So let's just think through what that's doing. If I can find some gamma, this is a scalar, right? So that when I subtract it from this polynomial, it's still sums of squares. And then I find the biggest, that means that I could also write this P of xy is, it's almost like I think I need a plus there, don't I? I want this to be greater. Okay, yeah, that's right. I got it right. I want P of xy to be greater than gamma. Okay, and then I want to find the biggest gamma for which this is true. So if I have my function of multiple variables with potentially complicated minima, and I say, here's my gamma, and I push up on this such that this thing is still sums of squares, then this is going to lift up and put gamma at the lowest value here. Even though that's a non-convex landscape, I can find its minimum value, or I can ask a question, can you find a minimum value using sums of squares? Now, because there's a gap between the sums of squares polynomials and the positive polynomials, I'm not guaranteed in every problem to find the exact minimum, but it'll always be a close approximation. Okay? And that's what I did in the example. I showed that in the six-hump camel, it basically finds the minimum up to some epsilon. So that's a surprising tool. Okay, so if you're paying attention here, so this is finding not the value of x and y that obtains the minimum value, it's finding the value. And oftentimes what you want is the value of x, or the particular xy that obtains the minimum value. Those are different questions. The sums of squares language, as I've written it, gives you the ability to find the minimal value, but not the minimizer. But you can take the dual of these problems and find the minimizer in most cases when things are tight. That's a detail that we won't get into, but okay. All right, so this just becomes a tool for checking positivity of polynomial functions. This one didn't have any additional, the coefficients here were all fixed, but it'll get more interesting if I didn't know if that was a 4 and I wanted to optimize over that value, for instance. That's what we're going to do in a minute. Questions about that? People like the thumbs up, yeah? Mostly thumbs up? Thumbs up you can do? It's a very powerful modeling tool. I'm going to step through some examples and some code in a second. Let me address one of the biggest questions that everybody has is, does this only work for polynomials? What do you think?
Yeah, the polynomials are a complete basis.
The polynomials are a complete basis. That is definitely true. So there are important properties of polynomials that make this work well. Having a very good understanding of the basis of generating polynomials and the like is absolutely one of those features.
Could you use like a Taylor series to approximate one of them?
Awesome. Good. So the question was, could you use a Taylor series approximation? So if I have a more complicated function, then you can take a Taylor series approximation to get a polynomial and then use these tools. Absolutely. Now, if you care about proving that your robot's not going to crash, right? If you're then you have to be careful with that Taylor approximation, right? But there are tools for many nonlinear functions to bound the error of the Taylor approximation. So you can do things like that for sure. I think the general answer is that theoretically it is not restricted to polynomials. So there are a few properties that make polynomials work well, and there's a few almost software things that make it polynomials extremely good. For instance, so what's important here? So it's a linear function approximator, right? So the fact that we can optimize over the coefficients makes polynomials a really good choice. That's a big deal. Yeah? Good. So the question is, would it work for discontinuous or piecewise functions? The fundamental modeling trick is this. You want to write your composition in a form that is positive by default. And then the second piece is to be able to do matching, coefficient matching, so that if you have a different function that someone gives you, you want to be able to equate it to this. I don't think there's anything, I mean, you'd have to find a class where it was practical, but even if you had discontinuities, you could play that trick. So I don't think discontinuities break it out of the box.
So when we do with that for like a certain interval where the function is continuous and then a different approximated each time.
Yeah, you would have to be able to somehow equate two discontinuous functions at all x. But if you could do, I mean, but you could imagine doing that, right? Certainly for simple, for a ReLU network that's, you know, that's got millions of activations, I don't think you should try. Right, so the basis is important, right? Known bases, you know, for mx, for instance, that's a big thing that we get out of having polynomials. Knowing how to do coefficient matching. You know, these are the practical things that make polynomials work so well. And also there's just a gobs of good theory about polynomials that we can lean on, like you know, all of the algebraic geometry that people know are able to give us like powerful bounds and understanding about these things. For instance, if I wanted to do this with sines and cosines, right? Equals some combination of other things that have sines and cosines. I mean, that's going to be an important one for us because our robots have sines and cosines in it, right? If you wanted to take an arbitrary functions of sines and cosines and ask it to be exactly equal to some other with free coefficients, then it's not that you can't do it, but you have to go through all the trig identities and everything to, you know, so you have to, like the software package has got to be a lot more complicated because sine of theta 1 plus theta 2, you can break up into, you know, all these different trig identities that could make coefficient matching harder. Yes?
I apologize if this is an office hours kind of question, but could you really quickly say again, what does it mean for something to be sums of squares? Like we're saying d of x is sums of squares?
Yes.
What does that mean?
Yes. So I want you to for a lot of, think of it as you know, approximately greater than or equal to 0, but what it means is that I can write the polynomial. So if I had v alpha of x, which was my, you know, whatever this, I could actually write it as something that has, you know, like 1 plus 2x in here plus some other thing. I can write it as a sum of terms that are all squared. That's what it means to be sum of squares. The way that we do that is by having a bunch of polynomials, of monomials in this, like x squared, x to the third, like this. Okay, I multiply this and I say that p has to be greater than or equal to 0. That is a way of writing positive squared combinations. Okay, it's a generalization where it's not strictly this form, but if that matrix is positive definite, then there's a factorization.
And this is significant because we know we can minimize the sum of the squares function.
The fact that this becomes a convex constraint means that we can ask this question for complicated polynomials, and the solver will be able to say yes or no. No, that's great. Yeah, I think also just, you know, lots of theory that we can build on, and there's lots of lots of details, lots of relaxations, lots of things to know, but it does not work only for polynomials. By the end of the class today, we'll talk about how I use it for trig, for sines and cosines. You can turn them into polynomials, okay? But in general, the idea can go farther. The tools tend to use polynomials. Okay, so let's work through an example. Back to Lyapunov specifically here. So we said, if we have a Lyapunov candidate, let's do the, verifying a Lyapunov candidate first. So if someone gives me a v of x that's polynomial, if I have f of x polynomial, then we said last time, right, that v dot of x will also be polynomial. It's nice in the sense that it stays in the class there. So if someone gives me a dynamical system, right, that says, for instance, like I have x1 So that's just a two-dimensional f, right? That's just x dot equals f of x, where x is x1, x2. It turns out that I know for this system, by the way, I can show the phase portrait here. That's the phase portrait of this system. It has a fixed point at the origin. Let me make that a little bigger. Okay, it's just some crazy vector field. This one was actually in Pablo's thesis. That's where I got it from. Okay, Pablo Pereira is the guy who made a lot of the connections for sums of squares and control and optimization. Pretty good thesis. So yeah, so this has got a fixed point at the origin, and it's got some complicated polynomial vector field, okay? And it turns out, we happen to know that v of x is x squared plus 2x1 squared plus 2x2 squared is a valid Lyapunov function for that, or at least that's my claim. And then I want to use sums of squares to certify that claim. Right, so I can't just check eigenvalues for this. I actually already need a solver to just check, is v dot, right? If I take v dot of x partial v partial x, that's not hard, times f of x. But that's going to get a complicated polynomial function and asking, is this less than equal to 0, right? Which I'm going to ask by saying, is sums of squares negative of that sums of squares? If I can find a sums of squares certificate for that, then I've proven that that is globally stable to the origin. Okay, I don't actually need to worry. This one is already a sum of squares by observation. I could tell the solver to verify that too, but I'm not even going to bother because that one's clearly positive. It's clearly radially unbounded. Okay, so let's just, also people have said in the comments that they wanted a little bit more about sort of how to use the modeling language, right? So I just make a mathematical program. I tell it to create x. It says new indeterminates, okay? So when I make these optimizations, the the variables x, I've erased the one I most need. Okay, even in this optimization, the decision variables that the solver knows about, it knows about gamma, I'm minimizing over gamma, and it makes a matrix in here that it's going to optimize over in the sums of squares. It's my sums of squares decomposition. But the variables x and y actually never enter the mind of the solver. The solver doesn't even know about x and y. X and y here, we call them not decision variables, but these are indeterminates. They're the things that we say for all x, for all y. They are not decision variables. They're just a construction that we use in the setup code, which we then pass to the solver. Okay? So in this code here, when I'm verifying a Lyapunov candidate, I need two indeterminates, x1 and x2. My dynamics, I just write as the equations of motion I just did, F. I say what my Lyapunov candidate is in terms of, it's just x squared plus 2x1 squared, okay? I can write v dot, I can just ask it to take the derivative for me. I don't have to do that myself. And then we have this modeling language now where we can say, mathematical program, add a sums of squares constraint, saying negative v dot is sums of squares. You just add that to the solver, call solve. If it's successful, if the program is feasible, then that means that it's certified the fact that that is a sums of squares polynomial, and we've successfully verified the Lyapunov candidate. Right, I actually did it. It's okay. Hooray! We successfully verified that that's a Lyapunov candidate. So this is the new capability, is this modeling language of saying, add a sums of squares constraint. And it's super, super powerful. Questions? Yes?
I can see that like for the dynamical system with like polynomial, like the Lyapunov like certificate is kind of like SAT, but when it comes to like general like nonlinear dynamics, how do you turn that into SAT?
Right, that's where I was trying to go with this. So we're going to definitely do trigonometric stuff, but I'll show you how to treat, it turns out that rigid body dynamics actually are polynomial. We typically write them with sines and cosines, but if you think about what it means to be a rigid body, it means that distance is preserved, and distance, Euclidean distance is actually just a quadratic thing. So there's always a way to take our robot dynamics and write them as polynomials. We just hide them behind sines and cosines normally. Yes, please.
So not every polynomial that is always possible is sums of squares. Right?
Correct.
What sorts of, are they important to polynomials that are not sums of squares but are positive all the time?
So the question is about the gap between sums of squares polynomials, and I'm repeating for the camera, yeah, for sums of squares positive polynomials and the positive polynomials. Right, so there are in theory, that gap is very important. And there are many possible gaps actually. So when we start searching for Lyapunov functions, for instance, there's another gap, which is that having a polynomial dynamical system that is stable cannot necessarily be proven stable with a polynomial Lyapunov function. That's another gap. But there's already a gap, just, yes, the positive polynomials and the non-negative polynomials. But that gap is very small. In practice, it seems that gap is very small. You have to work hard to find counterexamples. And because the expressiveness of the Lyapunov functions, where many Lyapunov functions can prove the same thing, then we tend to not be suffering that gap. We find polynomial Lyapunov functions for very complicated systems. Yes?
So just to clarify, like, is it true that like if we can find a sum of squares representation of the negative of v dot of x, that doesn't necessarily mean it's not?
Correct. Exactly. So you said exactly the right thing. So that the implication of that conversation is that if you have a system, you run this, and it fails to find a sums of squares polynomial, it does not mean it's unstable. It could still be that it's stable, but you failed to prove it.
I have a follow-up.
Yeah, please.
If I have a polynomial and I want to check if it's always positive, can I do that or is it hard?
It's hard.
How hard?
Yeah. NP hard. Yeah. Maybe worse? No, I think it should be NP hard, right? Yes. No, I think so. Univariate polynomials are special. You can do lots of things with them. Multivariable polynomials get hard. There's special cases. I mean, these are classic problems, but it's hard in general. Yeah, if you're quadratic in 2 variables, then you can do it. There's a couple special cases where it's okay. Yes.
I looked up something online before coming here. It says like this sum of square optimization, even like increasing the degree of the polynomial from 1 like slightly makes the problem extremely like hard. So, or are they like special cases where you can score higher?
Okay, good. So the question is, I read something online saying that things can get bad if you increase the degree of your polynomial.
Yeah.
So I do think that when you write polynomials in the standard form, and you try to make them more expressive by just adding more and more degrees, like if I want to have a really curvy function, if I were to write it like this, and I just write like x to the 14th power or whatever, then the numerics of that optimization get bad. That is absolutely true. So, but there are many different ways to parameterize polynomials. So you have to be wise in your choice, and also better. So the initial when sums of squares became a thing that people could try, a lot of people tried it and then gave up because the numerics got bad. Okay, but there's been progress. Some of it I had a PhD student that worked with Pablo and with me that worked just on his thesis was on making the front end better, so that it generated smarter polynomials to hand to or smarter SDPs to hand to the solver. Because there's still a lot of work to be done there in the modeling choices that you make. For instance, how do you pick the monomial basis, right? If you choose the monomial basis that has terms you don't need inside it, then you can make the numerics of your solver very bad. But progress there has made a huge difference in the numerical robustness of this. SDP solvers even are not as robust as LP and QP and other solvers. In general, they are not as mature of a technology as as LP, for instance. But
Sorry, earlier you said like all robotic systems are somewhat polynomial or something like that. So a comment in the back. Could you just clarify what you meant?
I'm going to clarify that with an example at the end, I promise. And it's rigid systems. I want to be careful. I mean, the soft stuff we can still talk about, but the thing I said was about rigid. Okay, good. So let's do something a little bit better. So everybody dislikes when I keep saying, oh, I just happen to know a Lyapunov function, right? So what if instead I said, I don't know the Lyapunov function, but I'm going to go ahead and search for it, right? I'm going to say it's like alpha 0 plus alpha 1 x1 plus alpha 2 x2. I'm just going to write a generic polynomial up to degree 2, or I could do higher degree, okay? And I'm going to say, can I search for the coefficients of that polynomial with sums of squares? Okay, so this is now the way that I search for Lyapunov functions, and I don't have to have a magical inspiration to come up with the Lyapunov function. So how does that change the optimization? Okay, I still just make my indeterminants x and my dynamics f. That first part's the same. But now instead of typing in a v, we're saying make a new general polynomial up to degree 2 using these variables. Okay, there's this new, the way I can do this is a new sums of squares polynomial. So we also have just a new polynomial that would generate exactly this. If I do a new sums of squares polynomial, it'll actually generate it in this quadratic form, which is by design positive. and it'll add the constraint. So all that happens behind the scenes when you just say make a new sums of squares polynomial. It's like saying make a new polynomial and add sauce constraint for polynomial, but it's a little more clever because it makes exactly the parameterization it needs. Okay. And then I basically do the same thing, but to make this problem a little bit better, I want to add two additional constraints. I say that v of 0 equals 0. That helps constrain the polynomial. So it could be moving all over the place. And just to give it a scaling, because I could take if v of if I have some Lyapunov function that proves negativity, if I multiply that by 2, that would also be a Lyapunov function for the system. So if you don't constrain the scaling, the solver might say, I want something crazy. So I do that by just take some other value somewhere in the system and just set it equal to 1, just to kind of set the scaling. Okay. Those are linear constraints because when I insert the value of x in here, I just get a linear combination of the coefficients. So I add linear constraint to set it equal to 0 and equal to 1. And then I just add my sums of squares constraint. Now this is doing the extra step of actually searching for a Lyapunov function with sums of squares. Okay. The candidate it search over, I made this like pretty LaTeX printing of mathematical stuff, but I didn't go in and change the default parameter of the variable name of that the sums of squares generates for you is symmetric. That's like, I'm like, oh, I made this LaTeX thing. It's all pretty, but then it says symmetric for the variable name. So next week it'll say something smarter than that. But bear with it. Apart from that, so this is before the candidate. I'm just saying these are decision variables: symmetric 2, 2, symmetric 1, 0. Right? They're parameterized. Those are the elements of that P matrix it made, which are by design symmetric. Okay, and those are the decision variables of the problem. And when I solve it, the polynomial I get out is, guess what? x1 squared plus x2, up to 6 decimal places. That's how we found that magical polynomial that I always just come up with. That's how we got it. X is not a decision variable. Those are indeterminates. I can actually even just let's ask the solver to list its decision variables. What are the decision variables? I have 2 sums of squares constraints flying around. So the decision variables are the coefficient. Oh, sorry, go ahead. Yes, it's the 2 coefficients of the 2 polynomials. So how many of them are there? All of these, the ones I wrote, the symmetric. So that went up to 2, 0. So there's the top triangular part of the symmetric are all decision variables. So there's all of those, but there's also the decision variables for the x. So x has a set of decision variables, and x dot has a set of decision variables. Sadly, I think if I print out the decision variables, they're all going to be called symmetric, probably. Oh, damn it. Yeah, I'm definitely going to fix that. But there you go. So the first symmetric are the ones that are the coefficients of v, and these are the coefficients of v dot across the matching. That's what the solver sees. It's trying to find those coefficients in order to certify this higher level, specification. Is that clear? Okay, ask questions. Yes?
Are the coefficients of v dot not dependent on the coefficients of v because it's a time derivative?
Awesome. Right, so that's the perfect question, right? So the question is, aren't the coefficients of v dot dependent on the coefficients of v, right? Yes, they are. When I generate this, I get this, this line in the middle here, which is the v dot is v Jacobian dot f, right? That I get some polynomial which has the coefficients of v inside it. But the way I write this as a sums of squares is I say that that polynomial equals some monomial basis, and I make additional new symmetric decision variables like P2. I make this as a new set of decision variables, and then I relate those two with equality constraints on the coefficients. That's the general modeling power. Because then I can write this and just say that matrix has to be positive definite. If I tried to populate that with all the coefficients, it's a much harder exercise. So I'm going to make these decision variables explicitly and then put linear constraints across. Great question. Other questions? Okay. You'll get to play with this on the problem set, and I think you'll be able to work through machinery. I mean, one person said about the PyTorch, you know, like it's frustrating to use Drake because Drake is act like a black box, but Drake's not a black box. Drake is an open source, fully documented code. It's like, you know, when I try to PR something to Drake, and if I have like a punctuation error in my comment, it gets rejected until I fix the punctuation. Like the documentation's really good, I think. The problem is you need to know where to look. I know that, and we're trying to make more like higher level, you know, directions or whatever. But if you find any method like here that you want to know more about, there's extensive documentation. Okay. For instance, yeah, like add sums of squares constraint. You know, there's all kinds of, there's a few variants. It's all fully documented. So please feel free to look at it. So I have this oracle which says I can, if I have a polynomial, you know, v alpha of x. Levi, you realize I'm trying super hard not to write p. He's like, you used p twice yesterday, and I was like, So every time I write p and then I erase it and I write p, but I'm trying. Okay, so if I have this oracle which says this is greater than or equal to 0, almost, it's sums of squares, then the question is, if I want to prove something about a basin of attraction, so remember my favorite example of x dot equals negative x plus x cubed, right, which is the one that goes like this, and it has a stable fixed point here, right? This is okay, and the basin of attraction of this fixed point is x in -1 to 1. I showed you when, you know, when I introduced Lyapunov functions that it turns out that v of x equals x squared is a good Lyapunov function, and I can use it to prove that. But can I do it with sums of squares? I have an oracle that will answer questions, is my polynomial positive everywhere for all x? But x squared, jeez, oh Pete, sorry. Can I just turn that one off? Can you guys hear me okay if I turn that off? Let me try. If it becomes hard to hear me, tell me, okay? V dot of x is not going to be negative everywhere. V dot of x does this something like this. So if I ask for v dot to be negative everywhere, you know, v dot of x that will fail on this problem. What I want to say is, can you find a region inside here where v dot of x is less than or equal to 0 and satisfies the conditions that we talked about for verifying a basin of attraction with Lyapunov. So there's another modeling step we need to make, which is to understand if you have an oracle, like in ancient Greece or something, you can go to the oracle and ask any question, and well, as long as the question is phrased, is my polynomial positive? Given an oracle that answers that question, how do you ask this question? Right? It's like one of those interview questions or something like there's two robots in a room and there's one door. How do you what question do you have to ask your oracle so that you can answer that question? The answer is you use a trick that looks a lot like Lagrange multipliers. Okay. That's called the S procedure in more general. Okay. Don't ask me why S. I learned the answer, but it's not satisfying. Especially because the people who, Sasha Magretsky is always joking. He says the people who invented S procedure are Russian, and the letter S isn't even in the Russian alphabet, so he doesn't really know how that happened. But it's got lots of other names, Nolenstaats and positive Nolenstaats and stuff. But we'll call it the S procedure. Okay. So let me ask a question. Let's say if I want to say if g of x is less than or equal to 0. This will be my new modeling question. For all x, let me call this my domain D, would be the set where g of x is less than or equal to 0. So I'll make a domain, I'll find some function that describes a domain of interest here. And I'll describe it by a polynomial, by the level set of a polynomial. Okay, if I want to say that g of x less than or equal to 0 implies that v of x, let me say, greater than or equal to 0, then the question you ask your polynomial oracle is, see, I keep writing p, v of alpha x plus lambda of x, g of x is sums of squares. Okay? And lambda of x is sums of squares. In general, if this could be a vector of constraints, and I could make a vector of multipliers. But let's just think about what this means. Okay, so make sure I get the sign right and everything. Okay, so when g of x when I'm inside this region, g of x, okay, this term is negative. This is the trick. This is like what you ask robot 1 and to get robot 2 to say the right thing. Okay, when I'm inside this function, this region, g of x is negative. This thing I make sure is positive. This thing I'm multiplying. This is just another new sums of squares polynomial. Okay. So I know that if I can prove that that whole sum is sums of squares, then it definitely must have been positive inside this region. Okay. Outside the region, this might have been negative, and that's okay because this one is positive outside the region. This is positive, so this is going to contribute a positive term. So this will help you be more positive, more sums of squares outside the region, and it will only hurt you from being sums of squares inside the region. Is that clear? This thing, less than 0, means that if you're inside the region, it's going to pull you to being more negative. Outside, it will help you be more positive. Therefore, if I certify this whole thing as sums of squares, then I know it must have at least been sums of squares inside the region. And it's possible, because this can help me outside the region, that even when this was negative, this will give me a yes. This is a lot like a Lagrange multiplier in optimization, but it's potentially not just a scalar, but another polynomial. And here's one that you might have read about. So the degree of this, so it is, you should be able to find polynomials. I won't go into all the theorems of it, but if you find a sufficiently high degree polynomial, then the gap is small, but you might have to make the degree of that high. This is what's unknown. In practice, we use small degrees and we get away with it for Lyapunov. Okay, so what I want to say is when I'm inside the region, v dot of x is less than 0. This is the model. Once you have that, you can start writing fancier Lyapunov conditions, saying like, for instance, when v is less than rho, I can do, I'm going to, the details here now are less important to me. If you get sort of that basic idea and you understand the modeling power of the sums of squares polynomials, then you've got the most important parts. Okay, the rest is about how do you massage the particular Lyapunov conditions that we've been writing down into those to use that new oracle that we have. Okay, and there's lots of details to know there, lots of good things to know, and I'll sketch them, but if you understand that much, you've gotten the most important part. So in that polynomial thing, what I'd like to say, for instance, is that when v of x less than or equal to 1 implies that v dot of x is less than or equal to 0. This is the equation I want to certify that v of x squared is a Lyapunov function in the region between -1 and 1. I want to say that when v of x is less than 1, v dot of x is less than 0. Okay? And I can write that down. There's a handful of ways to write that down. The simplest one is just directly what I wrote there. I can say, I can make lambda of x a new polynomial of some degree. I think I needed up to x4 for this particular example. And then I find c subject to the constraints that negative v dot of x plus lambda of x 1 minus v of x is sums of squares. If I can find the coefficients of lambda that certifies this, then I've certified that this is the set inside -1 and 1 is a region of attraction for that fixed point using optimization.
Why does lambda have to be polynomial? Why can't I just use a positive number?
Why does x have to be a polynomial and not be a, what's that?
Lambda.
I'm sorry, what is lambda? I pointed at lambda, I said x. Why is lambda restricted to be a polynomial and not just an arbitrary number? The intuition I gave you, of course, works for any function. But if I want this whole thing to be sums of squares, right, my modeling tool says I can ask if polynomials are sums of squares.
If lambda was just a real number, then also you can ask.
Oh, good. So lambda, in the simple case, it could be a scalar, but that is not powerful enough in general. That you can have functions that are true over the domain where lambda is not enough. You might actually have to increase the degree of lambda in order to, so so if I have g of x, let me think about exactly how to convince you of this. So this is my 1 minus v of x. No, it's not. This is my 1 minus v of x. Okay, and I want to say that this plus my v dot, which I said something like was this. I want to say that this thing, when I add them together, is positive everywhere. The function I chose goes down at some rate. The function I'm trying to certify is going up at some rate. It's not clear that just a scalar multiple of this is enough to kill the growth rate of this. In general, this thing needs to have enough degree power to grow faster than the thing it's trying to protect you from.
I thought you were trying to protect the I'll ask you later.
Yeah,
I'm
yeah.
confused.
It's a good question. It's a good question.
I thought you were trying to protect the finite inside part. So
You have to do both. In order to certify this for all x, you have to not break the inside, and you have to actually help me because this thing that I cared about was negative, so it couldn't possibly be sums of squares. So you actually also have enough power to make that positive. And if it's a scalar, if this is like degree 43 and this is degree 2, a scalar is not going to be enough for you to kill the growth rate of this. And that needs to be a higher degree. Now, oftentimes you can pick this to be so that the degrees match, but even that is not quite enough. But that's a good heuristic. That works a lot of times. So you can write this out, and I, of course, did. Regions of attraction for the one-dimensional cubic system. Verified that x squared less than 1 is in the region of attraction. Okay? It's like a few lines of code. I made a lambda be my new sums of squares polynomial. I added my sums of squares constraint. I knew I had a sign error here because when I drew that, that was upside down. This is a minus here. Or I could have flipped that around. Okay? But it's almost exactly that, that math, and it verifies. I can also, within some limitations, I can also search for Lyapunov functions. And in particular, let's say I didn't know the level set. I didn't know that I wanted v of x less than 1. I want to find a bigger or smaller region of attraction, because I don't even know where the region of attraction is. So I put in here, I hard-coded this v of x less than 1 implied this. But it's more interesting if I say v of x is less than some level set, implies this. And find me a row. Now we're into the stuff of finding regions of attraction. I can come up with a simple Lyapunov candidate and ask how big of a space can I verify those conditions? The bigger you can make row, the bigger the space you can verify. And we're gonna have you do that. There's a bunch of different formulations. We're gonna step you through on the Vanderpull problem. Okay, but it's only a few more lines of code to add a linear cost on row. You have to shuffle some things around to make it convex. But this is the modeling power. Yes?
I'm a little confused by what the alpha and d alpha actually is.
Those are the coefficients of the polynomial. So, for instance, if I were to have written this as, I might have put a little c here to represent the coefficients that I'm free to search over. Sometimes I'm trying to be explicit about remembering that we have coefficients in there that we can control. Okay, so I'll stop with the math of it and try to tell you what you can do with it, okay? So, like in practice, what kind of questions can you answer with this? If you're willing to now play these games of finding the right question to ask the oracle to answer these questions, optimizing the level set of the Lyapunov function, for instance, would be equivalent to finding regions of attraction. By the way, just like LQR, there's an LQR code in Drake. You can just call region of attraction for a lot of them now. I try to put the best implementation behind a black box, and you can just say, here's a system, here's a fixed point, find me the region of attraction. It's almost a technology. It'll be better technology after my PR lands tonight, hopefully. But so here's an example of the Vanderpull oscillator that you're going to work through at some length. Okay. So the Vanderpull oscillator is just another polynomial dynamical system. You can see the phase portrait that I've drawn here. The Vanderpull oscillator is famous for oscillating, I guess. And so when the phase portrait of the normal Vanderpull oscillator is such that if you start out here or you start in here, it will converge and the trajectories will go around in a circle or almost circle over and over again. So why is that an interesting one for asking regions of attraction question? If you take the equations of the Vanderpull oscillator and reverse time, it's a trick, so then basically the thing that was a stable fixed point here, the stable limit cycle, we'll talk about limit cycles, but this boundary here, suddenly where this, in the original time, this was an unstable fixed point, and there was only a limit cycle, and then it would converge from the outside. If I flip time around, this unstable limit cycle becomes stable, and its known region of attraction, known up to numerics, is the boundary that was the oscillator before. In reverse time, all the trajectories that start inside this region will converge to that fixed point, and all the ones outside will just blow up. So that's a very clever way to have like a non-trivial known region of attraction, and we can ask, how well can we estimate that region of attraction using sums of squares? And the answer is going to be, it depends how much modeling power you put in V. How high of a degree polynomial are you willing to search for? This is just an example of a quadratic. This is the quadratic V that's solved for automatically with no bells or whistles. If you just call region of attraction, it finds the quadratic V. This is V less than rho, for the biggest rho it could find, is the inside of that blue region. Okay, so what I want to make sure you understand is that the sums of squares is giving me a certification, but it's an inner approximation of the true region of attraction, right? So the true system we constructed here is the region of attraction is that black line. I asked to find a certificate of that, the biggest region of attraction I could find with a quadratic Lyapunov function and over some region, and it told me I can prove everything with a quadratic Lyapunov function up to here. You'll see I think in the problem set you go to the Quartic Lyapunov function. I think so. You'll see that you can get a much tighter version if you go up to Quartic. Okay? Let me go ahead to that. I think I've got that over here somewhere. Yeah. Look, I think that's the one you should be able to get with a degree 4 polynomial. Okay. It also depends the degree you choose for lambda. You have a couple. Those are now the knobs. It's not like tuning it's maybe your equivalent of hyperparameter tuning. You just pick the degree of lambda and the degree of v, and you can get better and better approximations. Okay. To make the point that these things don't have to be convex sets, right? The level set of a Quartic Lyapunov function is not necessarily a convex set in space. Just because we're using convex optimization does not mean we can only certify convex shapes of regions of attraction. Those are just different ideas. So this is an example where we constructed a known, some weird system that the orange region is the known region of attraction to the origin. I tried to certify it with various different approaches. This is a bad approach with a small proof of stability. This is a Quartic, I believe, also Lyapunov function that it found with sums of squares, okay, and it's not convex, right? There's 2 points inside that set that the combination of that is not convex. So this can find pretty non-trivial regions of attraction. Yes?
For the previous example, the region, what polynomial describes that region? Like, what would it be? Yeah.
This would be, I picked the same way I just wrote sort of an arbitrary polynomial out. I said, give me a polynomial up to degree 4.
Okay.
Find the coefficients of a polynomial up to degree 4.
I guess my confusion is we're looking for the quadratic Lyapunov function, right? Then if the g itself is like more than degree 2, then like how would you set up the SOS?
It all works. If you pick a degree for v, you pick a degree that implies a degree for v dot. You get a polynomial of some degree, and you ask for it to be sums of squares. The sums of squares is a combination. I think the thing maybe that's misleading, right, is when I make the sums of squares on the right-hand side, I'm able to put combinations up to arbitrary degrees in my sums of squares, right? So the polynomial that I certify can be arbitrary degree. It doesn't have to be quadratic. Okay, what about for robots, right? So remember the LQR controller we did for the quadrotor that was stable to the hovering fixed point from a lot of different initial conditions, right? So you can just take the equations of the quadrotor. In this case, I did use the Taylor approximation for this example, but I want to get rid of that in general, okay? I also have an LQR controller in here. So the thing I'm certifying is actually the closed loop dynamics of the LQR controller plus the quadrotor dynamics. I ask, can you find a region of attraction that certifies that fixed point over some big part of state space? And there's a couple different ellipses drawn here, but the first thing to notice is that these are highly non-trivial. They're not like small regions. This is able to prove big regions of state space are provably stable for the quadrotor. You can have versions that I'll step through in a second here of where there's uncertainty in the system. It's the robust stability, which is one of my last things, okay? Where I can ask, so let's say I didn't even know the mass of the quadrotor, or the wind is blowing plus or minus some degrees. You can put that into the equations too, okay? And it makes the region of attraction that it can certify smaller, but still very useful in practice. So that's one of the big ways we can use these tools. Remember how for the cart pole and stuff like this, we had pretty good energy controllers, but when we got to the top, we had to flip on the LQR controller? Well, there was kind of an arbitrary decision there of like, when do you know you're close enough to turn on the LQR controller? It doesn't have to be arbitrary anymore. I can certify that the LQR controller works over some big domain and wait until I get into that domain to turn on the controller, and I'm guaranteed I'll go there. Okay, I'll finish with one more point about the robustness of these things, okay? So here's an extension of that example, but let's just think about how would you ask about robust stability? And we already did it for the common Lyapunov functions for the linear systems. Remember that? We said that there was A was uncertain. It could have been many different values. I found a single Lyapunov function such that for all values of A, it was still going downhill. Well, let's do the same thing here. Let's take my favorite example, but I put a delta in front of there. So there's some coefficient of that x cubed that I don't know. All I know is that it's between 0.5 and 1.5. So what I can ask is, for all delta inside that region, using the S procedure, can I find a V dot that is going downhill? And you can. You can use all the same machinery to do this kind of thing. But just I want you to think about what this means. As I change delta, let me just plot that curve for a few different deltas. Okay? There's a handful of different curves depending on different values of delta. So the region of attraction that it's going to certify is only the one that works for all of them, right? So in finding a common Lyapunov function for all of these is like a worst case analysis. It says, I can guarantee you'll converge to the fixed point from these states. And that works for all delta in that region. And it's the same code, basically, with one extra S procedure to handle that. It gets more interesting, actually, when you have additive uncertainty. You would think additive uncertainty would be easier, almost. Okay, but if I have, like, I didn't know my equations up to some addition, that does funny things to your dynamical system, because the curves you get here are like this, right? So what fixed point are you stabilizing? You know, does that break everything? And the answer is no. You can ask for questions. You can still talk about you can't find a v dot that's going to converge all the way to the origin. But you can ask questions like, find the largest invariant set. So you can guarantee that once I get inside some region, I stay inside some region. It's a slightly different question with a slightly different question to the oracle, but it's all using the same kind of tools. Right? But it's important to realize that if your fixed point moves, you have to ask the question a little bit differently. And you can ask about invariant sets. So that's the modeling power that we've worked up to. Yeah? Questions? I mean, I didn't give you I don't intend to give you like all of the details of all of that. I mean, I give you code, actually. I have given you that. But you don't need to understand about every different permutation. What I want you to understand is that the general way of asking an oracle for these.
Can you go back to the non-convex region of attraction?
For the which one? This one.
Yeah. Is the blue, so what's the blue circle? That's the quadratic.
Yeah. So it's, I'm sorry I didn't label everything. So there's a couple different things here. Yeah, the blue was actually the quadratic Lyapunov function. It's interesting when you try to maximize the volume of a quartic. So when I started pushing out on the quartic, computing the volume of a quartic polynomial is actually hard. So you end up writing an objective, which is you try to push out on an ellipse that's inside the quartic as a surrogate for the volume of the quartic. So that's what this gray region is. It's just, I'm trying to explode out my volume with an inner ellipse, which is also something I can write in convex way.
So the quadratic is not included in the quartic.
Those are two separate optimizations. The little blue one was a separate optimization. I ran it once. I thought, that's pretty embarrassing. Let me try a better one like this. And I wrote the harder optimization with this notion of volume. And I got a much more satisfying region of attraction. I hope that the working through the details of the Vanderpull oscillator will be very fun and good, and we'll fill in the details. Okay, see you soon.